Welcome to the next video in this series, Survival Analysis in the Browser. Today we'll finally be training some survival models. The most common way to train a survival model is to use Cox regression. And all this does is it finds the contribution of each feature to the prediction, the risk. One trick you can use, however, is you can make a new feature, which is some transformation of an old feature, and then fit a Cox regression. The problem with this, though, is you have no idea what transformation you should do. And if you have multiple features, these transformations are going to be very complex, and there's basically an infinite number of possible transformations. So instead of trying to figure out what this transformation should be, you could just let a neural net figure that out on its own. And it can use the same exact loss as a Cox regression. The issue is that you don't really know what the neural net does. So let's see the differences between these two approaches. The Cox regression is going to be much faster, and you're also going to gain some extra information at the end of training. Lifelines will, for example, give you p-values for each feature, which you won't get for the neural net. And the downside, which we just mentioned, is the Cox regression only tells you the linear contributions, while the neural net doesn't tell you what it did, but it made some sort of complex transformation of the features. And since this model is simpler, there's going to be lower risk of overfitting, while there could be a very high risk of overfitting depending on your model and your features. So how about we investigate this ourselves? So let's go to Aliaxis, and let's first investigate how severe the overfitting problem is. So we have 500 samples, and overfitting, what it means is we have features, patterns learned in the training fold, which doesn't transfer to the test data. And so what we're going to do is we're going to have no relationship between our feature and the risk. So the only thing it can learn is noise, basically. And ideally, it should learn absolutely nothing. So let's see what happens. Let's make the data. Let's go ahead and just split the data. And we'll make a fairly simple model. Just have some soft plus activation. Our final layer needs to be a single unit and no activation. And I don't think we need bias here. We'll go ahead and monitor the C-index. We don't need to shuffle the data. And this will make it go a little faster. Okay, so there's a lot to digest on this page. So we'll go over it one at a time. This should finish pretty quickly. First, there's the loss. Now, this loss is identical to what you will get with Cox regression. The interesting thing about this loss, though, is it depends on the size of the data. So our train had 400 samples, but our test only has 100 samples. And that's why our test loss is lower. It's simply because of the difference in the sizes of the folds. So you can compare this loss directly to a Cox regression, assuming you use the exact same folds. And the predictions are also interesting to look at. The scale of the predictions does not matter. So this could be 12, this could be 20, it could be -10. What matters is the difference in the predictions. It's all relative to each other. And when you have noise, it's going to just do a random fit each time, which is what we had. Now, the question is, did we overfit? That was what we were trying to ask. So let's look at our evals. And the C-index for this fold is higher than the test, but it's not too high, and same for this one. And in this case, the test is actually higher. And here, they're about the same, and they're about the same here. So with a single feature and this many samples, you actually don't overfit that much with the neural net. So that's good to know, actually. But what happens if we have more than one feature? What happens if we have 10 features, and now all these 10 features have no relationship to the target? So ideally, we should learn nothing, but because we have more features, the model has the ability, a higher ability, to memorize the training data. So what I'm going to do this time is I'm actually going to monitor the C-index. The C-index I know caps at 1, and I don't know how low the loss is going to get. So if I change this to 0.01, this will stop at a 0.99 C-index if we get that high. So let's see what happens. Let's look at the C-index. No, we actually didn't get there. I didn't have enough. So actually, I'm going to go back because that stopped sooner than it should have. So I'm going to lower this a little bit and increase this too. Okay, the C-index should climb higher. Yeah, there we go. But I do want it to stop at some point. So you just have to play with your patience and your delta to get the model to stop where you want it to stop. So I think we saw what we wanted to see. So before, the C-index was about the same between train and test. Now the train C-index is almost all the way at 1, which basically means it completely memorized the train data. So when we have 10 features, we have a very severe overfitting problem. And let's just go ahead and quickly review what causes overfitting. So if you have a higher number of samples, we didn't test that in that example, but the more samples you have, the harder it will be to memorize all of them. And so you'll have less overfitting. The more features you have, or the more model complexity, we didn't test this, we only tested the features, then the more overfitting you'll observe. Now, the features, it also depends on how much information each feature has. For example, a single pixel in an image, which has the same value across all the images, contains 0 information. So that pixel won't help you overfit at all. So it really depends on how much information your features have, how many of them there are, and then how complex your model is. So how about we move on to some actual data? So let's actually open a new tab, another survival tab, head over to there. And this time, instead of generating data, let's get some actual data. So this is TCGA, mRNA, and survival data for all these cancers. It's actually kind of just interesting to look through some of this data. For example, sarcomas are connective tissue cancers, so they could be bone or muscle. And then you can look at a muscle-specific actin, and most of the time you'll see low expression, but then sometimes you'll see high expression. And these samples are probably the muscle tumors. So that's kind of interesting. But what we're going to do is look at a gene I'm familiar with. I've run Cox regressions on all this data in the past, so I know which genes have the strongest Cox regression values. And since the Cox regression values were so strong, I'm assuming the relationship is linear. So I would assume that the relationship in this cancer for this gene is linear. But of course, we don't know for sure because this is real data. We don't know the actual underlying relationship. So most of the values are around 1 and 3, but there probably are going to be some higher values in here. That's what typically happens with RNA-seq data. See, here's a 6. You're probably going to get some higher values if you look through here. And that can cause some issues as we'll see. So let's go ahead and submit that. And actually for this, it'll just go faster if we just train on all the data at one time. If you want to see a specific signal, the best thing to do is to train on as much data as possible, which is all the data. And looking at these label counts, we can see that we have 175 events in this data set. Now for the model, I'm actually just going to load a default FCN. So this is similar to what we just had, but now we have some dropout layers. The dropout layers prevent overfitting, but they reduce the power of the model. And I'm going to go ahead and take away the bias again for that. Now we'll monitor the C-index again. Always good to look at that. I honestly just want this to train for a while, but not go too crazy. I don't know. Let's see. Let's see what happens with that. Okay, let's see what happens. Okay, so this is interesting. Our predictions actually have a little bit of a curve to them. But if we look at this x-axis, we see the values go from 0.4 to 12. But we saw that most of the values are between 1 and 3. So you can kind of consider these values as out of prediction values, out of distribution values. And this is actually a common mistake in machine learning, deep learning, is making predictions on data which you didn't really train on. We trained mostly over here, and yet we're making predictions on data over here, which we had very few examples for. And yes, this is exciting to see a curve, but we have very little data to back this claim up. Unfortunately, you'll see this a lot in the literature. So let's fix this, and we can fix this by simply logging the data, because our distribution is probably a log normal distribution, and we can make it a normal distribution by taking the log. So now we'll try this again. And now our data is going to be more evenly distributed. And now with this more even distribution, we're seeing a straight line. But the question is was our model strong enough to detect a curve if one was present? So how about we go back to our simulated data, and we attempt to make some data similar to the real data, but with the curve. So let's see if we can accomplish that or not. So we had 531 samples, so let's do that. Let's go to label creation. Did we get, yep, see, we had 175 before, I think, so let's try to get similar amounts. It's close enough. And let's see what this looks like. That looks like it's too much. What did this look like? We got to go all the way back to the data. We got to get the data again. Okay, submit that, analysis. See, that's not as strong. Okay. Let's try to reduce this a little bit in our simulated data. Let's go back to the data. It's too much of a difference here. Okay. I could have just Oh, I see the problem. Yeah, so we need to do a normal distribution because we transformed the log normal to a normal. So we need to make a normal distribution for this data. And let's see how this looks. Okay. That's looking more similar. So let's just go ahead and use that. And again, we just want to see if we can pick up a signal or not. And we're actually going to go ahead and use the model without dropout. Or no, let's use the same model. Yeah, so we're doing a positive control, so we want the exact same model. And try to just have everything the same as we had in the other example. So let's see if we pick up this curve here. And we didn't really pick it up too much, but it did look like it was trying to. So maybe we need to actually just lower this a lot. And let's see. Yeah, it's not really picking it up. So let's go back to the model and let's remove the dropout. And then we'll try this again with no dropout. And now it is actually picking it up pretty highly. And it learned too much. So again, there's not that much data at the edges because we have a normal distribution. So there's not that much data here, not that much data here. But it did pick up the curve if we remove the dropout. So let's see if we can go back to our real data. And let's see if we make a model with no dropout if we see any difference. So let's take away the dropout for this real data. And let's now see if we pick up any signal at all for a curve. Nope, didn't pick up anything at all. Okay, so that was interesting. So what just happened here? So what we had was we started with some real data for TCGA. We assumed it was a linear relationship because the Cox regression was strong, which I knew before. We ran a neural net and we saw a linear relationship. But then we asked, what happens if we make some simulated data with this relationship and we fit a neural net? And we saw that we actually needed to remove the dropout to see this signal. So then we went back to the real data and we asked, okay, if we have no dropout here, what do we see? And we still saw a straight line. So most likely this real data is a straight line. So that's not too interesting. And actually, the difference between a straight line and this curve is also not too interesting. What you're really looking for is you want to see no relationship in the real data. And then when you fit a neural net, you want to see a very strong relationship like this. If you try to run a Cox on data like this, you'll actually get no relationship. Unfortunately, I don't know which genes show this pattern. And as far as I know, no one has ever run neural nets on the TCGA survival data. So that's up to someone to do eventually. It's a lot of compute to do it for every single gene, but if you have some genes you care about, you can see if they follow this pattern or not. And maybe you'll publish a paper on it. So hopefully you found that interesting. I don't think there's too many videos out there going over training survival models or training neural nets. Okay, thank you.